technologies, and we've already had the introduction to the session. I'd like to give you, it's about a 5-minute introduction to Marathon and what it is that Marathon does. And then we're going to get into the topics for the day, and that's primarily why do you need dryers at CNG stations, and it wasn't always clear to people why they are required. Then we're going to talk about what technologies are practical, because there are a number of alternatives out there. How do common CNG dryers work, then configurations of dryers, some data required so that you can specify a CNG dryer, and then we're going to entertain question and answer at the end. So as I mentioned, I'd like to give you a brief overview of Marathon Technical Services. We are solely involved in professional services for the compressed natural gas industry. We do not manufacture, we do not provide construction services directly, but we are North America's leading CNG consulting firm, and we do provide both technical and financial analysis for the compressed natural gas or CNG vehicle infrastructure market. Our staff has nearly 30 years of dedicated full-time experience in the CNG market. This is not a sideline for us. This is our primary market. We don't do other types of engineering or analysis. It's just related to CNG. And because of that focus, we have a long-term stake in the success of the CNG industry. In addition to our industry-leading experience, we also offer an impartial view of the suppliers that are out there. We have no affiliation with any equipment supplier. We work with owners to make sure that they get the best fit and best value for their project. We have a complete range of state-of-the-art analysis, project execution, and operation support tools and services. I'll touch on some of those as we go here. And we are a single consultant that can see the project through from concept right through to final operation. So this just is some sample output. This spreadsheet you see here, you won't be able to read it, but this is data that was collected on a fleet fueling. And we boil that data down into that bar graph that you see. We do detailed fleet fueling analysis, and we do a comprehensive sizing analysis, and from that we can project the budget. From the budget, we can do life cycle cost analysis, and so this is some output from one of those. And we test that analysis under various scenarios. And again, this is life cycle for a project. We can also provide management data. This was a breakdown of a cost of a gallon of gasoline equivalent for CNG, and the owner wanted to know where the costs were within that gallon. Our core business is really CNG station design and permitting, and we've done nearly 200 projects, CNG station projects across the U.S. and Canada, and pretty much every type of station that you can imagine. The one you're looking at here is a small transit station, and this is a unique site here because it was built on the side of a hill. We have, as I mentioned, significant experience in every type of CNG station. This one that's coming up here is a large public access station, a pretty new installation that we have, and actually it's right there in Columbus, Ohio, right where Clean Fuels Ohio is. We also do building upgrade audits. We do not do design of building upgrades, but we'll specify what upgrades might be required to facilitate use of CNG vehicles. Our staff have been responsible for a variety of innovations in the industry, and even things as fundamental as the design of transit fueling stations. We designed the first full-scale transit fueling station in North America, and that design has been widely copied even today, which is 25 years later. We try to deliver projects that provide safety, reliability, high performance, durability, scalability, and long-term value. This project you're looking at here is a trash fleet in Virginia. We use a full suite of design tools, including 3D CAD. So in terms of construction support, when the project moves beyond design and into construction, we do budgeting, scheduling, bid period support, submittal review for the contractor, site inspection during construction. We do equipment testing in the plant or on site, and we have commissioning oversight. And after construction, we carry through with operations support. So things such as safety and performance audits, design of maintenance and operation programs. We do forensic investigations, and this is not something that we necessarily want to do, but we have investigated a number of incidents in the industry. And of course, we do customized CNG infrastructure training, and that's what I'll be doing today. And some of the topics that we would cover in those are shown, but they are customized. We don't have a canned training program. We put training together based on the needs of the user. So we feel that Marathon understands the business of CNG, and our services can be summarized in this screen here. So I'm going to just escape this and start my next presentation here. This will focus just on drying. This is copyright, and we do have some disclaimers here as well in terms of the use of this material. So within a CNG station, there's a number of things that have to happen to the gas as it enters and leaves the station. First, we remove condensate and water vapor from the natural gas supply. That happens within the dryer. That's the portion of the station operation that the dryer handles. Then, of course, we compress it through the compressor. In many cases, we're doing some type of on-site storage, and then we're measuring and dispensing CNG. But it's number one that we're going to be focused on here today. So within the CNG station, you can see this is a compressor enclosure here. The storage is kind of hiding behind that, and this piece of equipment within the red box is the CNG dryer. So why do we dry natural gas? And I've been in the industry for about 30 years, and in earlier times in the industry, the utilities were of the opinion that maybe we didn't need to dry natural gas because their gas was already quite dry. And they're correct. The gas, at the pressures that they deal with their gas, it is quite dry. However, as you compress gas, it loses its ability to hold moisture. You can think of it as you're squeezing the moisture out of the gas. So as you get to higher and higher pressures, that gas that was relatively dry coming into the compressor can become relatively wet as it leaves the compressor. So this is the main thing behind the need for drying. Most gas in the U.S. is supplied at 7 pounds of water per million cubic feet. And so we'll show you a table here in a couple of slides from now and explain why that's a problem. So keep that 7 pounds of water per million cubic feet number in mind. If we have liquid water, we have two problems. One is that we may have internal freezing inside of a regulator or some sort of throttling valve. Any localized pressure drop could cause us some operational problem. So that's the first problem. The second problem is that liquid water, if combined with hydrogen sulfide or carbon dioxide in sufficient levels, can produce a corrosive effect inside of particularly carbon steel vessels, such as the storage vessels on site. And this could be quite a significant event if a failure occurred. Apart from those real-world reasons, we also have some code requirements that drive us towards the need for dryers. And the one that led off this was really, it's not a code, it's a recommendation. but it was produced by the Society of Automotive Engineers, and it's SAE J1616. And it's widely recognized and widely adopted across the industry in the U.S. And essentially what J1616 says is you have to have gas that is dry enough that at a dew point 10 degrees Fahrenheit below the minimum monthly temperature, basically that your gas is that dry. What is dew point? Well, dew point is the point at which the gas starts to condense water out of it. So we've all had the cold glass of some sort of drink with ice in it on a table, and you notice that dew forms on the side of that. Well, that's because the air around that glass is damp, and the cold glass lowers the temperature of the air right there to the dew point, and it condenses. Well, the same thing can happen inside of CNG equipment, and we're trying to avoid that by drying that gas, removing the water vapor down to a point where that can't happen. The other codes that are referenced here, California Air Resource Board and ISO, essentially have similar requirements. The CARB requirement is a little more severe because it's not looking at the monthly temperature. It looks at what is the coldest temperature any time through the year, and that's what you have to maintain. So, but they're all really looking at a 10-degree Fahrenheit reduction below what is required, or basically below the monthly temperature, excuse me. So I mentioned to you that 7 pounds of water per million cubic feet. And this table here will give you some idea of how that translates into the real world. So if you look primarily at this green column, because most CNG stations today will have a maximum pressure within the station of 4,500 psi. So if you're in Atlanta, based on its coldest climate, coldest temperature, January temperature here, -8, it means we have to have a -18 dew point. That corresponds to 0.45 pounds of water per million cubic feet. Again, remembering that typical pipeline quality is 7 pounds, it basically means we have to remove 6.5 pounds per million cubic feet that runs through the station. And you can see these numbers are all typically below 1 pound. There's Los Angeles, it's higher, and San Diego, Sacramento, they're a little bit higher. But even in, say, San Diego, which is the highest water content allowed because it's a warmer climate, even in San Diego, we would still have to dry gas to get it down to those levels. So that's the reason why we have to dry. There's both a code reason and there is also practical reasons and safety reasons. Then the issue is, well, how are we going to do this? By what means can we dry? And so here's a number of possible types of technologies, and we're going to talk about these various technologies in the next few slides. So early in the industry, people thought, well, I'm just going to put a coalescing filter on the inlet of my station and probably on the outlet of my station, and I'll take the water out by filtering it out. And a coalescing filter, you can see a cutaway of one here. Basically, you have dirty and or wet gas that enters, and in a coalescing filter, we actually introduce the gas on the inside of the element. That's not like particulate filters that many people would be familiar with. So coalescing filter, we introduce the gas on the inside, the gas flows out through the media, and any liquid, aerosol, will accumulate in that media, and it'll eventually bead up on the outside of the element and flow down the outside in droplet form. You can see some droplets here, and then it collects in the sump in the bottom, and that can be manually drained. So pretty straightforward, and we do use these for in the CNG stations primarily to filter oil out of the system. But the key thing here is coalescing filters do not filter vapor. Coalescing filters will only filter liquid, and it's in this case probably small droplets of liquid, which are aerosol. However, in CNG, to get rid of the water vapor, the water is primarily in vapor form. So we can't just filter it out. It's a vapor. A coalescing filter will not remove that vapor. So we have to find some other means by which to do that. So then the next thing might be, well, what about a refrigeration dryer? And these are commonly used with air compressor systems, and they're a very simple process. Basically, you're cooling the gas down to a point where the water vapor becomes liquid, and then you can filter it with that coalescing filter we just showed. The problem here is that these units will only, we're dealing with water, and so they will only really be effective down to temperatures of around 35 degrees Fahrenheit, because below that you would start to build up ice inside the unit and inside the filter. So that's impractical. So they are not used for CNG. And in fact, in the air industry, they're only used if the air is going to stay inside of a building. If you're running air outside of a building, you have to find some other type of dryer there as well. So the next one we're going to talk about is something called a deliquescent dryer. And deliquescent dryer is it's an interesting concept. It's a very simple piece of equipment. It's basically a tank, and you can see this tank here. We're flowing gas into the tank. It goes through a pre-filter here. It goes back up through a chamber, and this chamber is filled with pellets. And these pellets are the ones that I'm showing you with my mouse. Sorry, I just there we go with my mouse here. So these pellets are basically a salt and or organic compound pressed into pellet form. And as the wet gas flows through that deliquescent bed, those pellets will gradually dissolve, and the condensate will fall down into the bottom here. So you're pulling vapor out of the gas, and you can drain it. So far so good. They're very simple technology, but there are limitations as well. The appeal of them, they're very low equipment cost, they're low installation cost, there's no power required, and there's no moving parts. So that's the good part. The bad part is that really these only reduce the dew point of the gas about 10 to 20 degrees Fahrenheit. So in order to be most practical, these would be installed on the discharge of a compressor, because the gas is at its highest pressure there, and therefore it has reduced ability to hold moisture on the discharge of the compressor. So if we put it on the discharge of the compressor, the problem is we have we have temperatures coming off of the compressor that are generally 20 degrees Fahrenheit greater than ambient. So we have warm gas coming off the compressor. Even if we reduce the dew point 10 to 20 degrees, we're really just back to where we started, and so in effect we haven't taken any moisture out of the system. And these have been tried in CNG. I have been to installations where they were in use, and interestingly they weren't draining any liquid off the bottom, and they weren't adding any salt into the top, which means it's not really removing any liquid from the gas, any vapor from the gas, excuse me. There's other issues. If you had a dew point much below 32 degrees Fahrenheit, you could potentially freeze up in the bottom. Now it is salt, so it will depress it somewhat below freezing, but it will still freeze in cold climates. And essentially the bottom line here is we can't really achieve the pressure dew point that we require with this deliquescent technology, and so they are not widely used in the CNG industry. There is still some use of them, but it's very limited. So then the next possibility is, what if we dry using desiccant, but we dry on the high pressure side? And this is the way virtually every air dryer is positioned in air systems. And so it seems intuitive that we would use high pressure drying for natural gas as well. And then this has been tried, and it continues to be used in certain applications. The appeal of a high pressure dryer is, and you can see one on the upper right hand part of the screen here, a high pressure dryer has a very low equipment cost, very low installation cost. Again, there are no moving parts. It's just a tank full of desiccant. And by the way, desiccant is when you buy a piece of electronics, maybe or a camera or something like that, there's a little packet of desiccant that comes in the box, usually with that consumer good. That desiccant is there to keep the inside of the container dry. That's a desiccant called silica gel, usually, or activated alumina. The desiccant we use on CNG stations is called molecular sieve. But it's a similar idea, and it has a high affinity for moisture, so it will pull water vapor out of the gas. And the last reason why high-pressure desiccant dryers are appealing is we're drying on the high-pressure side of the compressor, where the gas itself has its lowest ability to hold moisture. So that's the good news. The bad news is that being on the downstream side of the compressor, if we have a lubricated CNG compressor with almost any amount of oil left in the gas, and there is likely to be some oil carryover from the compressor that will get past the filtration on the compressor, and almost any amount of oil that gets past the compressor will quickly foul the desiccant in these chambers. And these chambers are small. The ones that you're looking at on your screen there would be approximately 6 inches in diameter by about 2 feet high. So they are quite small. Because they're small, they also hold very little desiccant. And so, for example, you might have a 20-pound load of desiccant in this dryer that you're looking at here. Desiccant holds about 10% of its weight in water. So 20 pounds of desiccant holds about 2 pounds of water. And so you will very quickly saturate. And what we're saying is if you have design high-pressure dryers usually require disposal. Because they're passive, there is no regeneration system involved with these dryers, and that means when the desiccant becomes saturated with moisture, basically you have to throw it out. You pull it out of the tank of the cylinders there, and you dispose of it. It's disposed of as hazardous waste. But it's also wasteful because it could be regenerated if it were used with different equipment. So you're disposing of it. That's a cost, and maybe not the best environmental practice either. When you open that vessel to put new desiccant in, humidity will come into the vessel, and you'll get some humidity just even in the metal itself, especially steel. But also the new desiccant that you put in may pull moisture out of the air as you're pouring it into the dryer. And that's okay if you've got a regeneration system because you can just regenerate the dryer. But when you're essentially, this is like a cartridge here, and in this application, when it becomes saturated, basically if it's partially saturated before you start using it, you've just reduced the life of your desiccant charge. There is a possible practical application for this on a CNG station, and that would be if you have very low throughput stations, and also preferably if you have non-lubricated compressors at those sites. And those types of equipment do exist, but again, very limited applications and mostly for low throughput stations. So I just said if you could regenerate it, then that we wouldn't have to be disposing of this. Well, why not just use a regenerative high-pressure desiccant dryer? And the industry has been here before. This has been tried, and back in the 1990s, there was an attempt to use this technology. We have some of the same problems because, again, a lubricated compressor will foul a regenerative dryer just as it will a passive dryer. When you're putting this on the discharge of your compressor, and again your compressor is about discharge temperature is about 20 degrees Fahrenheit above ambient, so that reduces the dryer's effectiveness. It has to operate at relatively constant pressure, and so what this means is you end up putting a valve, a back pressure valve on your system, and you end up running your compressor at maximum pressure all the time, even if you don't technically need that to fill your vehicles. You're going to be operating at high pressure, and that has some inherent risk, more so than if we were operating at low pressure. There's really not that much cost advantage to this approach as compared to some of the other equipment that I'm going to show you here as we proceed. And so these dryers are referred to as pressure swing dryers. And what that means is they basically use low pressure gas to regenerate the bed. And I won't get into a schematic of what that looks like, but I want to make the point that it gets the low pressure gas by regulating high pressure gas down so that it's relatively dry. And the net effect of all this is it cannibalizes about 15% of your compressor flow. So if you have a 200 CFM compressor, you really only have a net flow through that compressor of 170 CFM. Even though you have to buy the bigger compressor and you have to provide the power for the bigger compressor, you're losing a chunk of that flow just to keep your dryer regenerating. And frequent cycling on these are cycling every few minutes, maybe every 30 to 60 minutes, and that leads to more valve maintenance requirements. So as I mentioned, the industry has tried this. In the 1990s, there were a number of these sold, and it was really an unsuccessful approach to drying. I'm not aware of any that are left in use today, and I know a number of the ones that were installed back in the 90s were fairly quickly removed and replaced by a low-pressure desiccant dryer, which we're going to talk about next. So how is gas dried in most stations? Well, we do use a desiccant dryer, but it's a low-pressure desiccant dryer that we are using. So what I'm going to do next is I'm going to show you what that dryer looks like in terms of how it functions. Just quickly walk through the various parts here. You can see in the top left-hand corner the gas inlet. We take it through a pre-filter, and this is actually a coalescing filter. We talked about that a few minutes ago. A coalescing filter removes basically, in this case, slugs of water or maybe even slugs of oil that might come down the gas stream. So we run through that coalescing filter, and then we go into one of two beds. And at any given time, one of these beds is online. Right now we're showing both in standby, which means they are both capable of being used for drying. But there's two beds shown here in this particular example. We have a cooler, we have a separator, heater, blower, an after filter, and that after filter is there because if the desiccant from this dryer breaks down, and it does tend to break down over time, if it breaks down and manages to get past out of the dryer and into the compressor, it can do damage to the compressor. So it's important that we have a high quality after filter as part of our dryer package. So I'm going to show you what happens as we start to flow some gas here. And you can see the gas flowing. Gas is starting to flow in the top through the pre-filter, and we've pressurized this line across the top. This valve would be open, meaning that this dryer, or this tower I should say, is actually in drying mode. So the gas just flows through the tower. There's no moving parts in terms of the actual drying operation. That's not true with the regeneration side, but the drying operation has no moving parts. So we just have a tank full of desiccant, and this desiccant looks like small pellets. It flows out the dryer and through this other valve, and then on downstream through the after filter and on into the compressor inlet. So again, we're drying on the inlet side of the CNG station. The first thing we're doing when the gas comes on site, after it's measured, the utility meter set would be up here. Downstream of the meter set, the first piece of large equipment is the dryer. So the drying side of it, as I said, it's a passive operation. No moving parts on the actual drying operation. So at some point, though, we have a saturated tower, and we have to regenerate our saturated tower. And so right now we're showing this left-hand tower is starting its regeneration cycle. And so what I'll do is I'll start with the blower down here. And so what we've done is we've stolen a little bit of gas off of the dry side of the drying tower. We're pulling a little bit of gas off of there. We're running it through the blower, and we're heating it up. And why are we doing that? Well, because hot gas has the ability to hold more moisture than ambient temperature or cooler gas. So we want to heat it up and make that gas, make the relative humidity of that gas very low so that it will pull moisture off the bed. So we use a blower because we have to have something to force the gas to flow through this bed and back into the line. We have to have some mechanical push to that gas because there's no pressure differential. So we push the gas through the heater and it flows through the bed. And by the way, some dryers may flow, this is called countercurrent. In other words, we're regenerating in the opposite direction to that we're drying in. Some dryers may dry in the opposite direction from top down, or may regenerate from top down, I should say. But the basic technology is the same. So the processes from one manufacturer to the next will vary a little, but the basic idea remains the same. So we run that gas from the heater through the bed, and then we run it into a cooler. So at the bottom here, we have hot, dry gas. By the time it gets to the top of this left-hand chamber, we have hot or warm wet gas because it has picked up moisture here in the bed, and now that continues on, and now we run it through a cooler. And the reason we run it through a cooler is we want to reduce its ability to hold moisture so that the moisture will fall out. And this moisture will fall out into this separator where it can be manually drained. From there, we run up and into basically the wet side of the process tower, the drying tower, and we just continue this loop constantly. So this is, we're running this regeneration heating loop here until we get about 350 to 400 degrees throughout the bed. So when this gas coming off the top here is 350 or maybe more degrees Fahrenheit, we know that we have regenerated the bed. And that's typically, could be up to 8-hour cycle to do that, or on the heating side, maybe 6-hour cycle. So that's the heating part of it, and that's where we're really driving the moisture off of a saturated bed. So I've walked through this. I'm going to step through these arrows. So once we have that that temperature breakthrough at the top, when we've got our 350 plus degrees at the top of on the top of that regenerating tower, now we want to cool the gas down in that tower. We want to cool the desiccant down more specifically. Well, why is that? Why not just leave it? Well, for a couple of reasons. One is that if we were to switch over and very quickly start using this tower for drying and it didn't have a chance to cool down, we would be putting gas, we would be putting wet gas through this tower. The desiccant would be so hot, we wouldn't have efficient drying, so we wouldn't remove any moisture. But what we would do is we would heat up the gas, and then we would be hitting our compressor with hot gas. And that hot gas could do real damage to the compressor because the compressor is designed for maybe 60 degree Fahrenheit inlet, and we might be introducing 300 degree Fahrenheit inlet. And so again, we would do damage to the internals of the compressor. So once that, that cool down part of the regeneration cycle is complete, once we've measured the temperature coming off of that bed to be something close to ambient, we'll shut down the regeneration cycle and we'll go back into a standby mode. And in standby mode, it really just means we're just sitting there waiting for this right-hand tower to saturate. And once it saturates, we have selector valves up here and down here that will reverse their position, and the left-hand tower will become the drying tower, and the right-hand tower will go into regeneration. So what does this look like? Well, this is a twin tower, fully automatic regeneration dryer, and this is the same dryer just from the reverse angle. There are several manufacturers of this equipment in North America, and you're going to see pictures of each of them in this presentation. And basically, again, we have these twin towers. We have the filters, inlet and outlet filters, as we mentioned. There they are. The blower sits inside of this this canister here. It's hermetically sealed. This vessel you see over here just catches the moisture that comes off of the separator. And then these two silver tubes that you see here, those house heater elements. And so those heater elements, again, they heat up the gas to as much as 400 degrees Fahrenheit. And then this is our cooler sitting up here. So this is one brand of equipment, and as I mentioned, I have pictures of several others. It's a 3D rendering of a larger version by the same company. This is Zeebeck. This is one of their competitors here, a company called PSB. Again, you can see the twin towers. Excuse me. You can see the twin drying towers here. This is your receiver here, I believe. Actually, this was the heater, the blower chamber, I should say. In the back, you can see the heaters here sticking out. These are control panels. And up in the top, it's mostly blocked, but your cooler is sitting up there. And one more manufacturer of similar equipment. So again, two towers. This is your cooler, your filters in and out, and tucked back in behind, I believe it's up in here, is the blower chamber. And as I said, your cooler. Notice these valves have actuators on them. So again, these dryers and it's a little bit lower cost, providing the same functionality. It's still a twin tower dryer, but in this particular case, it's a manually regenerated dryer. So by taking away the automated valves, we can save some money. The control system becomes cheaper. We save on all those expensive valves. The system becomes generally simpler, and in some cases, this is a very cost-effective and high reliability way of operating. Now, we still have on-skid regeneration. We still have our filters coming in and out. You can see them here. In this case, we have two towers. This is our cooler in the background. This is our blower in here. So we have regeneration equipment on the skid, but it has to be manually controlled. And so the dryer will operate. These are usually sized so they operate for about 3 months or 3 to 6 months, and then they require regeneration. Regeneration is about 8 hours, and in this case, you have a second tower, so you can operate on one tower while you regenerate the other one, and then you'll have once the regeneration is done, you can switch back when required. So this is one way to reduce some cost. And as we go through these various examples, we're sort of moving down in price. We started with the most expensive, which was the twin tower fully automatic. Now we've got a twin tower with manual regeneration. And the next step below that would be a single tower. A single tower with manual regeneration. And my computer seems to be stuck here. Just let me get running in here. There we go. So this is a single tower with manual regeneration. So again, we're just removing equipment each time we sort of step down in technology. And in this case, we still have the blower here, the cooler you can see up here. The heater in this case is vertically oriented. That's it. Filter is here and here. But now we just have one tower that we're using. Sorry, the filter's over here. We just have one tower that we're using to hold the desiccant. That's the same dryer from two angles. manufacturer's take on the same type of technology, but again, it's a single tower dryer, a manual regeneration. This dryer will operate, actually there's two different dryers here, but these dryers were sized so that they will operate, again, about 3 to 4 months in this case, between regenerations. And regeneration is about an 8-hour process, but it does not require that someone stand there for those 8 hours. They can initiate the regen and then go do something else and check back periodically. Again, here's your filters, the filter here and here, single tower. You can see, I'll switch over to this one. This is your blower housing here, a couple of control panels. Heater is laying horizontally in this one, and here's your cooler. Another manufacturer, again, same type of equipment, and again, this was sized for about a 3-month regeneration cycle, so it'll operate 3 months before you need to touch it. And while it's operating, it's a passive piece of equipment. There's really nothing to go wrong with it other than a possible leak. There's no mechanical equipment that runs on a day-to-day basis. And another picture from another manufacturer, again, the same type of equipment involved in this one as well. So then the next step down in terms of cost and in terms of package complexity is a single tower with no on-skid regeneration. And so regeneration happens with a secondary skid that is brought to site periodically. So you can see this is getting to be a very simple piece of equipment now. Basically, we just have a tower and some filters, and all of the complication is mounted on a regen skid. So here's a picture here, again, a different brand, but here's your single tower absorber. And so it's full of desiccant, and again, it would be sized so that it needed regeneration probably at 3 to 6 month intervals. Only this time when we want to regenerate it, we have to bring this piece of equipment on site, and we have all the same equipment here. Here's your cooler, here's your heater, blowers back in behind, and this is a tank here to hold condensate. You have to have a power source set up on site. You just plug in, and away you go. This fits in the back of the pickup truck. So for smaller stations, lower throughput or maybe medium-sized stations, this can be a very cost-effective approach because you're buying only one regen kit to handle a fair population of stations. So this is, again, a fairly simple and cost-effective way to address this need. So there's some information that you will require in order to specify a dryer. And this is by no means a specification that I'm giving you here, but it does give you an idea of the types of things you would need to give to the manufacturer to say, okay, this is essentially my application. Give me a recommendation for a dryer. And so the first thing I'm showing here is they need to know what the operating pressure range will be for this dryer. Next thing they need to know is what is an acceptable pressure drop across the dryer and filters. This is a piece of equipment on the inlet side of the station. We want to size it to minimize the pressure drop because if we have high pressure drop, we will reduce the amount of pressure that goes to the compressors, which basically means we'll also reduce the flow through the compressors. So we like to try to minimize that pressure drop. 5 psi differential is likely the highest that you're going to want to see on a dryer, and in many cases it's closer to 2 or 3 psi is what you might want to specify. The dryer manufacturer will need to know what your maximum flow through the dryer is going to be. So you need to look at your compressors and you need to say, okay, I have a compressor that is using or that is producing 200 CFM at 100 psi inlet pressure. So then you need to go back to the dryer manufacturer and say, okay, I have this application with 200 CFM at 100 psi. It's good to design in a little bit of contingency into that number. I usually add 10% to the flow, so you're going to have, in that case, you get a dryer that would handle at least 220 CFM while giving you this pressure drop that we're asking for, this 2 to 5 psi. The next thing is the maximum annual gas throughput. And this is not so much required on a automatic regen dryer, but it is on any of the manual regen dryers. And the reason is we need to know how big the tank needs to be, how much desiccant do we want in this tank so that we can hold the amount of moisture that is required with 3 months up to 6 months of running. And so that's the reason for the annual throughput. We want to determine how much gas is going to go through that in a 3 to 6 month period so that we can size the tower appropriately. The next thing is the water content of the gas. And this would be something that you would assume would be quite easy to come by, and sometimes it is, but often it isn't. Gas utilities may, in some cases, be able to provide this to you. I know some gas utilities will refer you to a lab and you can have the gas tested. That's potentially expensive, and it may not be as instructive as you would think, because when you go to the lab with your sample, for one thing, the moisture that's in the sample could be absorbed into the steel sample cylinder. Also, you're taking a sample in time, but that could go up and down over time. There may be periods where you get wet gas. And an example of that would be if there is cavern storage. And by cavern storage, we're referring to underground caverns where the utilities pump gas to be there to help them with peak demand periods. And this is done in several parts of the U.S. I know Ohio has some, New York has some. But you do have to be aware, if there's cavern storage, you could have some very wet gas, well above 7 pounds per million cubic feet, and we've seen gas above 100 pounds per million cubic feet of water. So that's extremely wet gas. It certainly will influence the type of dryer you're going to be using, and it'll influence the size of the tanks on the dryer. Basically, the flow throughput determines the size, the flow, I should say, determines the size of the piping and vessels on the dryer. The annual throughput determines the size of the actual towers themselves. So then what type of dryer? And by this I'm referring to, do we want to have a single tower without regeneration? Or do we want to have a single tower with a manual regen, or a twin tower with manual regen, or are we going to buy basically the top model and get the twin tower with automatic regen? And frankly, the twin tower with automatic is usually reserved for situations where we have high throughput, high flow, maybe a transit application, something along those lines. You're going to need block and bypass piping and valves on your dryer. That's often an option, although most dryers include a block and bypass around it. And you're going to need inlet and outlet filters, and again, that is actually typically a standard item, but you need to make sure you have them, that they're properly sized for your application. And then there's some instrumentation and safety equipment. The dryer manufacturers will have their own standard package of equipment, but there may be some safeties that you or your engineers are recommending be added to that standard package. And with that, basically that's the end of the formal presentation here, but we want to open it up to questions that you may have.
Thanks a lot, Rob. And if anyone has any questions,
any questions here.
Yeah, I don't see any either. So if anyone has any questions, feel free to type them into the little drop-down bar on your toolbar, and we'll wait a moment to see if there's any questions. All right, well, seeing as there are no questions, everyone, if you do have a question, feel free to take Rob's information down there. His email address and phone number can be found below. And thanks again, Rob. It was a very good presentation, and I certainly learned a lot, and I hope that everyone else did as well. I will go ahead and take the presenter mode away. Put it back to mine.
Thank you for joining the presentation, and I hope it was helpful for you. And as Lucas said, please feel free to call me or email me if you have questions that come up later.
Great. Thank you so much. Okay. All right. Well, I will be sending out another registration link for next month's webinar, which will be a continuation of CNG station technologies with another guest presenter. I'll send that out along with a link to the recording of this webinar through the NGV partnership email list distribution. We hope to see some of you tomorrow at our Dayton NGV Day. A lot of the Clean Fuels Ohio staff have been working really hard on that event, and we're looking forward to having a full house for that too. Thanks again for the participation today, guys, and I will see all of you all soon. Thanks a lot.